Okay, so in this talk I'm going to tell you about geometric recursion. And so it's a joint work together with Gaëtan Bourreau and Nicolas Aurentin. And so it's a kind of machinery that takes its origin in topological recursion, and we kind of think of it as a categorification of it in some sense. And I'll try to explain to you what I mean by that. So the basic idea is that it should be a recursive construction of the following kind of object, namely to sigma, and I'll tell you what sigma is in a second, it associates some omega sigma in some vector space that's canonically associated to sigma, and then invariant part. So this here is an object in a category of surfaces, which I'm going to tell you about in a second. And this here, E, is a functor from this category. I'm going to give it the beautiful name board 1 dot. So it's a functor from board 1 dot to some kind of topological vector spaces. And the topology will be important here. And this is a functor, so therefore, when you look at the mapping class group of any of the surfaces, they will act on these vector spaces. And I want that it is an invariant vector. So it's a machinery that can construct such invariant vectors. Okay. Now, you may think that that's maybe a little bit esoteric, you know, I mean, but I would say that almost anything I can think of in low-dimensional geometry and topology fits the scheme. So let me just give you a few examples. So this is sigma here. This is a compact, oriented surface, say with boundary. And then, so this is an example. And I'm going to introduce Teichmüller space of sigma. So this is the space of metrics on sigma with curvature -1 and boundaries, geodesics. And then you divide by the diffeomorphisms of the surface, which are isotopic to the identity. So that's the Teichmüller space of the surface. And what I take E to be of the surface, it's simply just, say, continuous functions on Teichmüller space. And then I think you will all agree that if I associate in there the function 1 to every surface, so my omega sigma will simply be equal to 1, then this is a perfect good example of such a situation up here. It may seem totally ridiculous, but this one will be a highly interesting case. But of course, you may not care so much about that single one function here. Maybe you like the following function a little bit better. So let S prime sigma be the set of all isotopy classes. Well, actually, maybe all multicurves in Thurston's way of thinking of it. And so I just say this in word. Multicurves are isotopy classes of one-dimensional submanifolds. None of the two components are isotopic, and none of the components are isotopic to the boundary. That's multicurves. And so I'm also going to give myself a function from the positive reals to the reals, and then I'm going to define the following function, f of some surface, just some smooth surface like this, that's going to be the sum over all possible gammas in the surface, so a sum over this set here, and then I take t to the number of components of each of the guys, so I write that like this, and then I take the product c equals, for all connected components of the curve, and then I take f of the length, and so this is a function on Teichmüller space, so it's at some sigma. This is the length with respect to sigma, so sigma is running in Teichmüller space of the surface. So I take this function here. So I allow the empty multicurve, and I interpret the product for the empty multicurve to be 1. So this function starts with 1 plus t, and then it sums over all gamma simple closed curve of the same expression. Maybe I should write it so you can read simple closed curves. And then plus t squared, and then the guys that have 2 components plus t to the third, and 3 components, and so on. And of course there's an upper bound to that for any given surface, because you could at most have 3g minus 3 curves plus number of boundaries curves that do not intersect, that is, that forms this one-dimensional submanifold. And such no two are isotopic. So this function here is a very interesting function over the moduli space, right? That is, clearly it is, so provided f here has good decay, so if f decays faster than, these truck are breaking, faster than any polynomial, then this here is an absolute convergent series, and so it is clearly mapping class group invariant, so this guy here really lives in the invariant part of continuous functions on Teichmüller space with respect to the mapping class group, so clearly it is a continuous function on the moduli space of the surface. Okay.
Is the multicurve, is it a curve with some class of recursion and so on?
Yes, I mean, I could have chosen to written it down if I wanted to. But I said it in words to save time. But since you ask, multicurve is isotopic classes of one-dimensional submanifolds. Submanifolds such that no 2 components are isotopic, and no component is isotopic to component of the boundary of sigma. So that's precisely what the definition is.
And what's the length?
And the length is that you take any such guy has unique geometric geodetic representative if you have a hyperbolic metric. And so that's the length. You apply the function, then you can consider this function here. And so it is a polynomial t for any given surface, but if you take uniformly over all surfaces, it can arbitrary higher power of t. But that's right, I was saying that it's, it has degree at most, 3g minus 3 plus the number of boundary components, where g is the genus. But so these are interesting functions, and one of the things that you can do is you can look at the expectation value, or maybe just, in this case, the average, and so this is defined to be sum over this moduli space of the surface, and then the function, with respect to the natural invariant measure that this guy has. And likewise over here, you can do the same thing here with this guy. So this is integration over moduli space of this function. And so this one here gives you the volumes of moduli space, okay? And these volumes were computed by Mirzakhani, her beautiful work in relation to her generalization of the McShane identity. And so this will play extremely important role in what I'm going to say, but it's completely open question how to compute these averages here in this generality. And if I get to the end of the talk, I'll give you the answer to this, because the machinery spits this out. Let's see. Oh, so cannot do two at a time. Okay, but you know, this machinery, I mean, so there are many more examples. So for example, there is forms on Teichmüller space, which are mapping class group invariant. I guess we'll put a little further. And there is all kinds of things. Just think about it. I don't want to waste time on somehow going through all the examples I have in mind. You know, if you want, ask me after. Let me now try to do the precise category on which this is defined. So board 1 dot. So what are these surfaces that I precisely want? So I want the following surfaces. I take one, for each connected component of the surface, I take one in and the rest out. Like this. It's a compact oriented surface, and each of the boundary components has an orientation. And this one here, they disagree, and here they agree. So therefore, there is a sort of negative boundary on this surface. By the way, the objects, I will write them like this. So let me try to do that, a bold sigma. So there's one in, and the rest is out. So that's the positive and the negative boundary. If I have several connected components, I want precisely one in for each connected component, and the rest out. I further want a point specified on each of the boundary components, like this. Okay.
The points are numbered.
The points are not numbered.
Oh.
The points are just there. Okay. And morphisms of these things are isotopy classes of diffeomorphisms that preserves all the structure you see here. So both the diffeos and the isotopies have to preserve all the structure. And the point about these points here is that up to isotopy, there's now a unique way to glue these surfaces. Okay, so I just say that this is objects, and for morphisms, I just say isotopy classes. Classes of diffeos, which preserve the structure, all structure. So that's the category I'm going to work with. That's no problem. And I just said before, I can glue things here. Now, yes?
Is the positive boundary assumed to be not empty?
No. But the negative one is. Okay. Because I required that there was a bijection between pi 0 of the negative boundary and pi 0 of the surface. And so unless the whole object is empty, then right. Okay. So now the target. What is the target? What is the target theory? So target theory is simply a functor. So a functor E from board 1 dot. So dot means the mark points. 1 means there's one in. So there's a singled out first boundary, or that in boundary. 2. The category of Hausdorff complete locally convex topological vector spaces. So that's the precise one we want. Okay, and now what do I require more about this theory? Well, I would like to know what happens when I have unions. So if I take disjoint unions of surfaces, I want to know that my theory has a bilinear map like this. And so because I'm working with these topological vector spaces, I don't want to specify any tensor products, so I just say bilinear map like this to the disjoint union.
You said functor, so...
Yes?
So what are morphisms on the left? Isomorphisms?
Isotopic classes are diffeomorphisms which preserve all structure. So they need to go to linear maps on this side, which are continuous with respect to the topology. Okay. Now, so notice that if I can, so remember my objective is to construct these invariant vectors. So if I can do so for connected surfaces, then I can just use these maps here to define them for disconnected surfaces. So let's, we just need to focus on connected surfaces, really. But you'll see that it's important that we both focus on both, because our recursion will go through disconnected surfaces also. Okay, now the gluing. So the gluing is simply specified by saying I take a subset of pi 0 of the plus part of the first surface cross pi 0 of the second surface in. And so I want this to be disjoint pairs. So in other words, if I take, another guy here, say, and I take one here, all that I'm just saying is that, and he has his mark point here and so on, all that I'm saying is just that you are paired with you and he's paired with him. Okay. And so because we have this mark point, there is a sort of unique way to do that up to isotopy. So that's all fine in relation to our equivalences. And so if we have that, what we want is a linear map, again, a bilinear map, I'm sorry, from the cross product to the glued surface, so E of the glued surface. And the glued surface I'm going to denote E union sub B along this pair of, or the set of pairs like this. So I need these two things to be given to me as a target theory. But I require, it doesn't make sense to say linearity in B, but I require this map here is linear from there, bilinear from there to here. That's what I'm saying. Okay, so this is a target theory.
Do you require continuity?
Yes, they are bilinear continuous maps. Correct. Okay, good. Now, so we want, as we know, right? We want to try to find this guy here, specify it somehow, whoops, inside this, in some target theory, and it should be exactly such that it is invariant. I mean, it should be in a functorial assignment, and a functorial assignment will automatically mean that it lies in the invariant part. And so, contrary to what we do very generally, say in quantum field theory and so on, is that we have something given on the whole space, and then we look at things on one side of a cutting, look at things on the other side of cutting, and that gives vectors that we take inner product of in the middle, and then maybe we say the whole thing is totally independent of the way we cut. And therefore we get something that's mapping class group invariant. Because one cutting is just taken to another by the mapping class group, maybe up to finite ambiguity as it is here. But that's not the way we want to proceed here. What we want to proceed here is just sum over all possibilities. And the possibilities we want to consider is the following. I'm going to take P to be the set of pairs of pants embedded in the surface, okay, up to, well, such that if I look at, so let me say, the pants, the generic pants will be called P, such that if I look at the minus boundary of the pants, this is exactly the minus boundary of the surface. So I guess right now I'm thinking of sigma to be connected. Because we've already agreed if I can solve the problem for connected surfaces, I can, via the gluing maps, or via the disjoint products, solve it in general. So set a pair of pants embedded in this up to isotopy. So I want to look at this infinite but countable set of all pairs of pants up to isotopy in the surface. And then, so let me make a little drawing here. So maybe I have some surface like this, maybe it's indeed closed, doesn't matter. But here is, say, one pair of pants. So this is the pair of pants. This is the whole surface here. And maybe I am going to call the complement C. Okay. So, by the way, there are sort of three distinct topological types of this nature here. So there's namely case 1, case 2, and case 3. So case 2 is where the pair of pants has two boundary components in common with the whole surface, and the situation looks like this. So I'm going to call this a B case. Okay, so here is, say, the minus boundary, so that's also the minus boundary of the pair of pants. And then there's an extra boundary component that's from the plus boundary, and that's also the plus boundary of P, and then there has an internal curve here. Okay, another possibility is that I see a C. Actually, this was what I drew up there. So I'm going to call that a C prime. So then I cut like this. Here's the pair of pants, and the rest is here. And the feature here is that this surface is connected still, because the last case is where the pair of pants somehow splits off like this. So here's the pair of pants. I cut this off. There's some topology here, maybe an extra hole here, like that. So I'm going to call this C prime and this C double prime. So there are three topological distinct types of pair of pants that I encounter here. Okay, good. So now I simply want to try to just explore the possibility to make the following definition recursively. So
before you do recursion, is the rest always simpler in certain sense? Is there an order?
Yeah, in what sense is it simpler? If you compute the Euler characteristic, which is 2 minus 2g plus n, minus n, then you will see that the Euler characteristic of the remaining piece is going up. So therefore there is a basis for making a recursion this way by summing of all ways of taking pair pants out and assuming that I already defined them for this. Okay, so that's indeed exactly what I want to do. So I want to say, let's try to just make this a sum of all pair pants of type 1 of the surface, and then I take the gluing map with respect to the pairing that I have of points, I mean gluing back sigma c, right? And then I take some initial data. This is going to be part of my initial data. So let me just write it out and then discuss where it's lying. This is something I assume I have already defined because it's of higher Euler characteristic. Plus, and I sum over P2 of sigma, and then I do theta BP C prime of P and omega of the remaining stuff. And you can imagine the last term, of course, P3 of sigma, and then theta B of P, and then C double prime, say, omega sigma C. Now, there is a little sort of thing in order to compare well with topological recursion. These two classes here are not distinguished in the recursion, the topological recursion. So I want to match with that for some reason. So therefore, actually, I'm going to make the simplification that in this case here, C1P is going to be the same as C2P. Okay, but in general, all I see is just that I have to pick some element in E of P here, and then it has to be mapping class group invariant, in this case of C. But then in the case of B, I don't have to require quite as much because there is a distinguished role that the two boundary components play. So there's kind of a B here, a boundary component. So I just need to know that it's invariant under the mapping class group that preserves this guy, or said in another way, I just need that B with an upper B, which I wrote here, signifying that that's the little boundary I have here. Like that, satisfies the following transformation rule. So this guy is also in the vector space of the three-hole guy, or the pants. But now it only satisfies the following, that if I have an element of the mapping class, of this, then that should just be B of phi of P, B. So if I have this property, then what will happen is that if I can make sense of these sums here, and if they are absolutely convergent, then I can turn the terms in the sum around as I like. And that's precisely what an element of the mapping class group is doing. It's just permuting all of these terms here. So if it's absolutely convergent, I will actually get something that's mapping class group invariant. Okay. Now, of course, the recursion has to stop somewhere. And I'm going to stop at the following place. So I'm going to say, yeah? What? There's no time to backing up, but just ask Renat. Oh, sorry. Yeah?
Can you make a 1 minute summary exactly of what are you doing? Because I follow the step, but then I'm kind of lost in the foot.
We could hope that we're defining 2D quantum gravity.
You're constructing geometrical quantum field theory.
Yeah, but it's one that's global, so it's probably like gravity.
But global in the sense, I mean, do I understand correctly that you construct from this functor that moves sigma to omega sigma?
Can I?
Sigma is invariant with respect to the lattice.
Yes, so will you allow me to fill out this board here with more formal stuff, and then I will step back and look.
Okay.
Because we're just before the conclusion. So where do we stop? Well, I'm going to stop when if I see some, in the end here, if I see some pair of pants, okay, I stop and I specify some element for there. So I have further initial data here. And then also, for some reason, I also want to stop if I see a one-hole torus. So I'm going to take dt to be some element in E of t. And t is just what you think it is, this guy here. One-hole torus with some point on the boundary. And then the recursion will work if I can do the make sense of the sums. And now the theorem is the following. And so, yeah, there are certain analytic conditions on A, B, sorry. So A of P, B of PB, C of P, and D of T. So analytic conditions on these. So it's a joint analytic condition on this, which is the initial data, and the gluing maps, theta B, such that this sum, so this sum I mean the sum there, such that omega sigma here is well defined, and the sum is absolutely convergent for all the seminorms, which gives you the topology in the vector space, and omega sigma lies in the invariant part of this vector space under the mapping class group. Okay, so now we can step back and look a little bit. So initially we wanted to have some assignment in some vector spaces. So first we have a functor that goes from surfaces with boundary, with mark points on the boundaries, and this little bit of orientation data, to vector spaces, and that should be functorial. And now we would like to build mapping class group invariant vectors inside these vector spaces. And the way that we intend to do this is simply to iteratively take out pairs of pants from the surface. Assume that we already have defined the vectors for the lower complexity surface via Euler characteristic, and then there are three different cases which causes us to make this sum over there. And then obviously, since these are infinite sums, we have to do some analysis to make sure that this is a well-defined thing. And I am saying that there exist some very specific analytic conditions on these, which I didn't write up on the board because I don't have time, but I will give you an example where I can really show you what the conditions are, namely related to what I wrote in the beginning for Teichmüller space. And then when these analytic conditions are satisfied, you get actually these vectors. Yeah?
Do you already start with the functor E given?
Yeah, so let's look at that. What is required for this machinery to work? What is required is that you have a target theory. That is this functor E, which satisfies this. And then you have to come up with initial data, A, B, C, D. And then if it satisfies certain analytic conditions, I haven't told you what it is, then the machinery will run and give you invariant vectors for your target theory.
Can we apply the same to construction of the functor E itself?
No, I don't think so. E must be given by some other means. So example of E is this one here, right? This is a good example of E. This is continuous functions on Teichmüller space. So actually, why don't we go back to that now? And I run an example where we run the machinery for that. Yeah?
Before we do this, are there any other examples?
Yeah. So, I mean, I can do the rest of the talk with examples if you want. So, let me read them out. Is that maybe okay?
Before you lose, do you understand correctly that these omegas that you get at the end,
Yeah.
that they satisfy kind of natural gluing condition?
Yeah. No.
No?
They don't. They don't satisfy sort of simple gluing conditions. Because they satisfy this recursion, which is a non-trivial thing.
You have intuition of where this came from?
We came up with it. So here are the symplectic, the Weil-Petterson symplectic form on Teichmüller space, the complex structure on Teichmüller space, the higher degree forms on Teichmüller space, mapping class group invariant cohomology classes of Teichmüller space, so cohomology classes of moduli space of curves, the Goldman symplectic form on moduli spaces of flat connections.
You're listing examples.
Yes? Oh, you asked for them, right? So complex structures on moduli space of flat connections, Ricci potentials on moduli space flat connections, the Hitchin connection, representations of mapping class groups can be thought of as invariant vectors. If anybody is puzzled, I can try to explain. Universal invariance of finite types of knots over surfaces that are mapping class group invariant. So of course that's the link to Kolja here. So in the old days we built actually universal invariance of knots in intervals over surfaces. But the constructions we have are not mapping class group invariant. But this could be obtained this way. But the target theory fits. Boundary vectors in Heegaard-Fleur homology, invariance of three manifolds via Heegaard-Fleur, via Heegaard splittings, invariance of four manifolds via trisections, cohomology classes coming from Gromov-Witten theory, amplitudes in bosonic string theory. I stopped there.
So in some sense, it's like a quantum field theory, but which satisfies, instead of gluing, this recursion relations.
It satisfied what I think should be satisfied if you want a theory of gravity.
So it's a non-local.
Yes, it's non-local. It's non-local.
Can you introduce some weights in this recursion in such a way that somehow this theory can be deformed into something local, maybe less intuitive, local? Are there terms in this recursion that is a simple gluing?
Yes and no. Because let's suppose you have some theory that actually is totally invariant under the splitting. So that means each time you split the surface and you stick in your vector for one component, you stick in the vector for the other component and you glue, you get the same thing. Then there is actually a way to take that invariant situation and use the Mirzakhani-McShane initial data to combine it with that to get it to fit in this. So there's a way that if it's invariant, you can make it fit in this. I don't know if you have something that fits in this could be made into something that is independent of how you cut it. And there is a gluing that says that no matter how I cut, I get the object. That I don't know. Okay.
But the mapping class group won't mix up the sums of these three parts.
That's correct. That's correct.
Write alpha, beta, and gamma in front of these sums and get something up.
Correct. Correct. But those can be absorbed in B and C prime, right? So I can just perturb my, right? Okay. Now, let me give you some examples because time is running and you will not see any of the beautiful analysis that's needed to do this. But you didn't want that because you want to solve. Okay, so let's do some examples because that's maybe more fun. So what we need to do is we need to look a little bit at Teichmüller theory. So if we take the example of Teichmüller theory, so in other words, what I'm doing is I'm letting E of this surface be the Teichmüller space, continuous functions on Teichmüller space. Okay? Now, let's compute what's the Teichmüller space of a pair of pants. Well, I'm looking at hyperbolic metric of on pair of pants, right? And so they're uniquely specified by the lengths of the three boundaries. So the Teichmüller space in that case is simply just r bigger than or equal to 0 to the 3. So it's canonically isomorphic to this by just measuring the length of the boundaries. Notice that I do actually allow that the length is 0 here in this way of looking at it. So that just corresponds to a cusp. Okay. But if I want to have perfect gluing conditions, I have to remove it. So let me remove it anyway. Okay. Now, so therefore, what's clear, right, is that A and B and C, they are just going to be functions of three variables, L1, L2, and L3. So here's the pair of pants. And I have L1 here, L2 here, and L3 here. Okay. So let me see if I can find them. Yeah, there are lots of good stuff we skipped. So this function here is 1.
That's a condition.
Now that's a stipulation. Okay, that's a stipulation. I'm giving you an example of this system of this. So I get to specify A, B, C, and D. Okay. So now this here, and I don't want to write all the coordinates because it's a function of three coordinates. 1 minus 1 over L1, ln of cos hyperbolic to L2 half, plus cos hyperbolic to L1 plus L3 half, divided by cos hyperbolic to L2 over 2 plus cos hyperbolic to L1 minus L3 half. And C is equal to 1 over L1 ln of exp of L1 over 2 plus exp of L2 plus L3 divided by exp of minus L1 over 2 plus exp of L2 plus L3. Same thing. Over 2, like that. And then D, I don't have a closed formula expression for D, but it is the following. You take the sum over all simple closed curves on the torus. So this is in the one-hole torus, right? So there are many curves that splits this guy into a pair of pants. And you sum over all of them. And what you take is C So this function here, and you evaluate it like this. You say L1, L, comma L, where this guy here has length L1, and this guy has length L. So this is obviously a function on Teichmüller space, right? So I should say a function of a point in Teichmüller space is the length of the boundary plus the length of this curve over there. That's the functions. Okay, and now theorem. Maybe I write the theorem over here. And so I want to call this initial data something. And so this is Mirzakhani-McShane initial data. And the functions, the gluing disjoint map is obvious. Teichmüller space of a disjoint union is just a cross product of Teichmüller space, so just pull back and product. Teichmüller space, when you glue, is just a sub-variety inside the cross product of the pieces where the lengths of the boundaries agree, so you just restrict the product to that. Those are the gluing maps and the disjoint union maps. So when you run the recursion with these data, then theorem, and I would say, yeah, okay, theorem, omega sigma is equal to 1. So this is an identity which says that if you, recursively, because it says that if you sum over all pair pans inside the surface of the B and C contributions, because the guy over on the right is already 1 by induction, then that identity that you see there, that's the Mirzakhani identity. And she generalized it from McShane's identity, which was in genus 1. Okay, now, the interesting thing about this is that if you then go on from this and you say, what I want to do now is I want to look at integrals, so this guy. So now what I want to do is I want to define V, G, comma N, the genus and the number of boundary components, and it only depends on the length of the boundaries. And you take omega sigma here, and you integrate it with respect to the Liouville measure that the moduli space has. So you define it like this. So that's just the volume. It's just the volume of the moduli space. Okay, and so what Mirzakhani actually did was that she used this formula for 1 to get a recursion on the volumes. Okay. Now, this recursion on the volumes can be formulated the following way. There is a way to take this initial data here and produce initial data for topological recursion. Then you run topological recursion and you follow it by Laplace transform. Then you will get those guys. So now this gives us an option to really seriously generalize her work. Because what we're going to try to do is see if we can come up with generalizations of this theorem here. A, we'll see if we can come up with generalized identities, and B, we'll see if we integrate the functions, what kind of recursion formulas do we get for expectation values. And so that's precisely what geometric recursion can do. So I'm going to take hold of, oh, whoops. I guess I won't pull that one down. So I wish you could use both at the same time, but that's not possible. That was too fast. Okay, so what I want to do now is I want to come back to this function here. So the question is, can I find an identity which actually gives a formula for that function when I run geometric recursion? In other words, can I compute this function using geometric recursion? You know, and I noticed that this function is very, very interesting because if I, for example, let f be a step function, it is exactly counting the number of geodesics, simple closed geodesics with lengths within some bound, And if you have two components, it's, you know, whatever the statistics is, right? So therefore, if I can compute these, and second of all, if I can integrate them over moduli space, I can say something about statistics of, you know, length of geodesics. So here's the point. So now we do F sigma. So what we have to do is the following. So I have to give you, but first of all, we notice that this function here is clearly multiplicative under disjoint union, even though it's a sum. Okay. But now I'm going to specify initial data such that when I run geometric recursion, I will get exactly this formula here, get this function here. So the initial data is the following, and it depends on f, right, because the function depends on f. So it is, again, of three variables, right? And so this one here is b of L1, L2, L3, and this b is just Mirzakhani's b, plus t times f of L. So a very simple t deformation of her initial data. Cf of L1, L2, L3. This is equal to C of L1 to L3 plus t times, and then b of hers times f of L2 plus b of L1, where you switch the two factors, and then you still use b of L3, or f of L3, plus t squared, and then f of L2 times f of L3.
But in the top form, we have a small l in the right side,
Yes,
but not on the left.
that is fully correct. And that's because in my notes it's written differently, but I decided I wanted to use L1, L2, L3. Okay, yeah?
That is correct that A is 1.
A is 1. And notice that that also fits, because if you take a pair of pants, okay? If you take a pair of pants, then there are no curves in a pair of pants that isn't isotopic to the boundary. That is a closed curve. So that function just returns 1 for A still. So that's the next thing I was going to write. AF is still 1. And then dt, which is now, you know, it's a point in Teichmüller space because that's just the way it is. So that's ft of sigma. This is just, by definition, the function it is. 1 plus t times gamma. And now I'm running through simple closed curves, gamma. Because I cannot have more than one component on that guy. And then f of L sigma of gamma. So that's this guy. So then when we run geometric recursion, so gr on this gives omega sigma equal to f sigma. So it means we can build these functions using geometric recursion. So that's, you know, you can think of this as a sort of generalization of the Mirzakhani identity. It's a t deformation of it that all of a sudden has these very interesting functions involved in it. Okay. Now, of course, you will not be surprised now, I think, that what I'm going to do now is just to integrate them over moduli space and see if I can come up with some nice statement about that. And so if I define Vf of g comma n, again it depends on length, L1 up to Ln. Now this is of course just the same as over there. I take mgn, L1 up to Ln, and then I take the function f sigma, and I take the Liouville measure on the surface. So I just take the average of these functions. And now the theorem is the following theorem. And so, let me, okay. So, you know, the real statement is that, that those integrals are, can be given by topological recursion. So it means that it's very easy to compute all of these iteratively in G and N. But let me actually write down explicitly what the recursion relation is. So the first thing is that I will actually give you exactly what D is. So D of L we can compute explicitly. It's L squared over 24 plus pi squared over 6 plus T times the integral from 0 to infinity of f of L, L dl. So D is explicit. Or if you like, this is also the same as, so this is also Vf1, 1 of L, right? Okay. Sorry, what?
Do you have some dilogated in the middle with pi squared over 6?
Yeah, it's a volume computational moduli space because what always is going to be here is it's the volumes. Yeah. So the first term will satisfy the same recursions as Mirzakhani's did. But there, you know, because there's this polynomial in T, then there's sort of this funny mix of all the terms. Now, so then in the second recursion, and this is a recursion just in these numbers here, or functions. So that says Vfg, n of L1 up to Ln. This is summing m equals 2 to n, integral over positive numbers of Bf, so the function from over there, L1, Lm, L, and then Vfg n minus 1, and then you stick in L at the first one, and you just leave out Lm, and then L dl. Sorry. That's that one, plus a half, integral over R positive real number squared, then C L1, L prime. And then you have sort of this whole thing where so it's basically going through the three cases that we have looked at before, L2 up to Ln, plus, and then you split the genus. So you split the genus G1 plus G2 is equal to G, and you write J1 disjoint union J2 is equal to the numbers from 2 to n. So you're just splitting the number of boundary components in two pieces, and then you take the product of Vf G1, 1 plus J1 size, and then L of J1 times Vf G2, 1 plus J2. And this should remind me a lot about topological recursion. And then L prime, dl prime. Like this. So there is the following recursion that these amplitudes satisfies. So therefore, if you want, you can just start computing them as you like. And so, yeah. As I said, you know, if you're interested in how many percent, which percent of the moduli space has geodesics that lie between 1 and 2 in length, and say you also want to know that there are two geodesics, one that is of length between 5 and 7 and another one between 3 and 4, then you can do that. All sorts of things can be computed like this. So you can do sort of multi-statistics of geodesic length functions. If I can find it real quickly, I will actually give you initial data for the Weil-Petterson symplectic form on Teichmüller space. Because it's kind of nice, because it illustrates what Kolja was talking about. But I have to work with slightly different Teichmüller spaces. And so you have to guess them, because I won't give them to you. But it's obvious which ones it are if you think about that the surfaces have these mark points on the boundary. So you just don't allow full isotopies at the boundaries, but you allow that, require that the isotopy preserves the point. And so if you do that, you get new Teichmüller spaces that are a little bigger. So I just want to show you this as a new theory, as a case where we apply to forms on Teichmüller space, so you don't believe it's only Teichmüller space and continuous functions. So if I take this new Teichmüller space that I just sort of mentioned in words, it's actually isomorphic to R plus cross U1 to the 3. And the U1 is because I've modded out by Dehn twists along the boundary components. So therefore, the extra R factor that really is rose up to a U1 factor. And so if you have that, you're going to take the following. A is going to be exp of I equals 1 to 3 d theta, where it's d li, where you have coordinates here, li, comma theta I, on this space here, I equals 1, 2, 3. And then B is simply B of Mirzakhani, L2, L3. And then you take exp of I equals 1, 2, d theta I, where it's d li. And then you take wedge d of theta 3 divided by L3. There's no way you can land that. And then C is simply C of Mirzakhani. And then you take exp of d theta 1, where it's d L1, which, and then d of theta 2 over L2, which d of theta 3 over L3. And then d is exp of d theta, where it's dl, plus d phi, where it's dl. And so phi, no, okay. So I just write it up here. So if you have a one-hole torus, what you will get is you will get L and theta at the boundary, and then here you have L and you have the twist along this is phi. And so this is the Weil-Petterson form written in French and Nielsen coordinates, and you exponentiate it. And now if you take all of this initial data and you run GR, then you will get that omega sigma is simply exp of the Weil-Petterson symplectic form. And the point is that when you unravel the recursion, what you will find is you're looking constantly at pair-pans decomposition of the surface. And when you look at the form parts, they all come out to be this one constantly. Because in French and Nielsen coordinates, it's always just given as some d theta I, where it's dli. And so therefore, these terms out here exactly takes care of the whole thing summing to 1 and becomes summable. And so this way you can get the forms like, for example, these closed forms. But as I said in the beginning, and when Corey asked me, I listed many things that I believe can be put in this formalism. They certainly form target theories, and that was what we were talking about, but that's his point. But it gives nice results in statistics and geodesics, and I think many more things. So I invite you all to have a look. Just Google geometric recursion. If you Google GR, it won't work. But I hope we can change that over time. Thank you.